In this presentation, we continue to talk about waves, and specifically we're going to focus on interference between waves, beats, and the Doppler effect. So interference occurs when two waves exist at the same place at the same time, and the results of those two waves overlap with one another. It's called superposition. And so in this particular little animation, I've got waves coming towards one another, and where they meet, the overall effect is that those waves can add together. So I've got a large amplitude, and then they go back to normal as they pass by one another. In this particular picture, I've made a short video of a PhET simulation that also shows interference. So I have two speakers, and those speakers are sending out sound waves, and we know that sound waves are pressure waves. Over on the right, once I start the video, there is a device that measures the pressure, and I've got these two probes that are set up at different locations. So let's go ahead and start this short video. We can see the sound waves are traveling out, and the probe that's located right here shows that the amplitude of that pressure wave at this particular location is very large, has a very large amplitude. So if I were to put a microphone right here, it would pick up a very loud sound that was occurring from these two speakers. On the other hand, at this particular location of the probe, you'll notice that the amplitude of the wave is almost zero. So if I were to put a microphone right here, the sound would be very low. We may not hear it at all. So we can have a situation where these two waves, these two sound waves from these speakers are interfering with one another. They're existing at the same place at the same time. Sometimes they're existing at a location where when they meet, they're in phase with one another, and we're going to see this, and they create a very large amplitude. And then there's other locations where they can almost completely cancel out. And then there's locations in between, which I don't show in this video, where the amplitude would just be less if I were to move the probes between these two locations. So this is interference between two waves. One of the things that's nice about this particular picture is that these speakers are vibrating with one another, and they both are vibrating at the same frequency. So to get this complete cancellation, the two waves have to have the same frequency. So one type of interference is constructive interference, and constructive interference occurs when two waves actually reinforce one another. And what happens is that the two waves are in phase, so they look exactly like one another, so that when one wave is a minimum, the other one is a minimum, and when one wave is a maximum, the other is a maximum. So if you superimpose these on one another, they would add together, and the overall effect at the location where they were both minimums would be a larger amplitude, and then where they meet at the maximum over here and you add them together, you would have a large amplitude. So constructive interference, the waves are in phase, but at any particular location, the waves add together. So even when there is zero pressure, let's say if it was a sound wave here and here, there's zero pressure here, and any place in between, let's say I was adding the waves at this location, I would add the value for the one wave and add the value for the other wave, and I would end up getting some value over here for the total wave. Destructive interference, on the other hand, occurs when the two waves are 180 degrees out of phase with one another. And the way you could think about it is they are mirrors of one another, so that when one wave is a maximum, the other wave is a minimum. And when you add those two results together, you can think about the top wave here as having a negative value, or the bottom one as a positive value. And when you add them together, you get zero. The same thing occurs basically at every location. They are mirrors, and so when you add those two waves together, it ends up giving you zero. So you can have destructive interference. So the amplitude of the resultant wave essentially is exactly zero. So we can see this in a simulation. And so I'm going to put this back to the values that I would have started with. And what this shows, make sure I got this correct. So both of these waves, I have two waves, wave 1 and wave 2, and this is showing what they look like when they are at the same place at the same time. And in this particular picture, they are in phase with one another. And the resultant of these two waves is up at the top. And so if I look at the location where they're a maximum together and I added these two values together, it would give me this new amplitude over here. But what happens is as these waves are no longer in phase with one another and they're shifted, we can watch what happens to the resultant or the superposition of those two waves at the top when they interfere with one another. And what's happening is that the amplitude of the wave is decreasing because now when wave 1 is a maximum, let's say at this location, wave 2 is not quite a minimum, but it's negative, and when I add those two values together, it decreases the overall amplitude of the wave. Now eventually, when they are exactly 180 degrees out of phase with one another, if I add these two together, the resultant, of course, is 0. So this would be destructive interference when they're 180 degrees out of phase, and then I would have constructive interference when they're in phase, and every place in between is just interference, right? Where they're interfering with one another, they are, the two waves are adding together where one might be positive and the other one might be negative. One of the things that's really important to think about as we look at this is both of these waves have the same frequency, and that's why they can cancel each other out completely, and also the fact that they both have the same amplitude. They both have an amplitude of 60. So if I increase the amplitude of one of the waves, then the waves can no longer cancel each other out, but of course I don't get the same effect I had when they were in phase with one another, because wave 1 has a large amplitude, wave 2 has a smaller amplitude, but it's negative, and so the overall effect here is that it is smaller. One example that we're all familiar with in terms of destructive interference is noise-canceling headphones. And so, we're all familiar with Beats headphones, and of course now there's the iPods, I guess is what they're called. And so a lot of those earphones are set up so that they have noise canceling, so that the ambient noise outside is canceled out when you're listening to music or whatever it is you're listening to. And the way that those noise canceling headphones work is you've got the ambient noise that's going in, and then you've got a microphone that picks up that noise. And then the microphone, and then there's of course electronic components in there that will create a signal that is exactly out of phase with the ambient noise that's coming in, and it causes those two waves to completely cancel out, and so you don't hear those sounds that are outside of the headphones. And that's destructive interference. Another example of interference is something called beats. And beats occurs when you have at least one example of beats occurs when you have two frequency sources, and in this case sound is a good example. So I have two tuning forks, and those two tuning forks have slightly different frequencies from one another. And so the two waves still interact with one another, but what happens is that I'm going to sort of focus on the top picture first. There are some regions where the two waves completely cancel out and you get destructive interference. So this is a rarefaction from one of the tuning forks and a condensation for the other. And then there's a region where they meet together where they're both a high pressure region. And then there's regions in between where they don't completely cancel out, but there's still some effect. And so this is still interference, but the waves are just slightly different frequencies. And so we have these regions where the two waves completely cancel out. This is the location right here, and it's moving. And then there's another location where the two waves meet so that they're always in phase with one another at that particular point, and that would be a larger amplitude there. So I have a website that sort of allows us to look at that, but let's go ahead first and just look at this a little more carefully. So this is a picture that sort of shows these two waves that have slightly different frequencies. So here's wave 1 and wave 2, and then we superimpose those two waves on one another. So we've got wave 1, which is blue, and wave 2, which is, I think it's pink. And so when we superimpose them on one another, we find regions like right here where those two waves are basically meeting so that their amplitudes are in phase with one another. Their maximums are in phase with one another. And if I come down to the superimposed interference pattern down here, I have an overall large amplitude. And then there's other regions, like right here, where the two waves meet so that they're exactly out of phase, and at that point they have destructive interferences occurring, and so they cancel each other out. And then there's regions in between where they don't completely cancel each other out, but they slowly, reach a point where they cancel each other out. And so if we were listening to a sound of these two tuning forks vibrating together, what we would hear is we would hear the sound get louder and then soft, and then louder and then soft, and louder and then soft. So that's an example of beats where two waves are interfering with one another, and those two waves have slightly different frequencies. So let's see if we can take a look at that website. So this is a nice website. So it shows the waves similar to that picture that we just had, and then the resultant wave. But what's nice about this is that at the bottom you can actually put in some frequencies, and you can hear what that sound would sound like, what the beats would sound like. Because I'm recording this video using headphones, it doesn't work very well to try to do this. So I'm going to provide this website if you want to take a look at this and try to hear those particular beats.